Let's now write the code for this weighted quick union method. The first thing we will do is to initialize the component ID array or the parent array, which is basically going to be a one-dimensional array of size n with indices from 0 to n minus 1. As you might recall, when we start off, each vertex is in its own connected component, so the parent IDs are basically going to look like this. Remember that our vertex IDs are from 0 to n minus 1, and so in the initialization phase we just set the parent of each vertex to be itself. So each vertex is basically its own connected component. And then we are going to start looking at each edge one by one as it comes in. So we will say for each edge u comma v that comes in, we will do a find operation on the endpoints of that edge to figure out who the two leaders are. So let's say root of u is the leader of the component to which vertex u belongs, root of v is the leader of the component to which vertex v belongs. Now if the two leaders are the same, then nothing is going to change in our data structure, but if they are not the same, if root of u is not equal to root of v, then we basically have to unify the two connected components together, and in order to do that we need to figure out which component is larger in size. So in addition to a parent array, we will also need another array for each vertex, let's call it size, which is also going to be a one-dimensional array of size n, and this is going to denote the size of the subtree that is rooted at that vertex. So initially each vertex lies in its own connected component, so the size of each component, the size of the component that is rooted at vertex I is going to be just 1. So the size array is just a one-dimensional array of size n initialized to 1. Now when we are thinking of unifying the components to which vertices u and v belong, we are going to compare the sizes of these two trees, and this size information is going to be stored in the size array at the indices corresponding to root u and root v. Remember that the size information for each vertex is basically the number of vertices or the size of the subtree which is rooted at that vertex. And so we really have to look up the index root u and root v to figure out the sizes of these two trees. So there are two options. Either the size of root u is less than the size of root v, and this could be less than or equal to, but let's say it's less than, then we know that we have to basically make the parent of root u to be root v. So we're going to set the parent of root u to be root v. And once this left tree has become a child of root v, we know that the size of root v has now gone up. So the size of root v will now go up by an amount that is equal to the size of root u, because the entire tree which was rooted at root u has now come under root v. So we have to update the size information like this. Now what if the other tree was bigger in size? What if this tree which is rooted at root u was bigger in size? In that case we want to do the converse. We want to make root v the child of root u. So we'll set the parent of root v to be root u, and if that happens, then we basically increase the size of root u by the size of this entire subtree, which is now going to become its child. So we say that the size of root u is now going to go up by an amount that is equal to the size of root v, the newly acquired subtree under it. And that's it. We just keep repeating this process for each edge that comes in, and at the end, after seeing all the edges, we would have a collection of disjoint trees, and we are going to call this collection of disjoint trees as the union find data structure. So the union find data structure is basically a collection of balanced trees which are storing a dynamically changing collection of objects or vertices in this case. As new edges come in, we might end up unifying some of these components together, and so it's a dynamically changing data structure, and at the very end, after we have seen all the edges, the number of trees we will have in this collection is going to be exactly equal to the number of connected components in the final graph. So if we have to keep track of the number of components, again we can initialize the number of components to be n, the number of vertices at the beginning, and every time we do a union operation, this is the code for doing the union, every time we do a union operation we can decrement the number of components by 1. And so at the very end, when after we exit the for loop, we would know the final number of connected components at this point. So if we had to return the number of connected components in the graph at the end, we could return it here, but as we saw, we could do the same thing using BFS or DFS. Where this union find data structure really helps is when we have to dynamically update the number of connected components at each step and keep printing out or outputting that information. If we had to do it only one time at the end, we could have solved this problem using BFS or DFS. Although, as you can see here, the code for union find is straightforward enough. We're not building an adjacency list or anything. We're not writing a function to do BFS or DFS from an individual source. We don't have an outer loop. We basically iterate over each edge, and every time we see that the endpoints belong to different union find trees, we unify those two trees together, we merge those connected components together, and because of that, the code for union find might actually run as fast or sometimes even faster than the code for doing BFS or DFS, even where you want just the final answer at the end. If you want an answer after each edge has come in, then you have no choice except to do union find. BFS and DFS are not efficient options, but even where you have to just return a one-time answer at the end, union find can often be a good alternative to doing BFS or DFS. Now, this is in spite of the fact that the complexity of this code is going to be given by the same expression that we had earlier. The number of union operations times a constant. The number of union operations is going to be at most n minus 1, and the number of find operations, which will be roughly 2m in number, times log n. And if you recall, we had derived this expression order n plus m log n in general, and we said that when the graph is sparse, this is basically order of n log n. Now, order of n log n is the cost for doing all of this, right? At the end, if you have to return the number of connected components, this is the amount of time it took. Whereas if we had to return the answer at the end only one time, then by doing BFS or DFS, we had a complexity of order m plus n, which was basically order n for a sparse graph. So you can see that union find is theoretically a little more expensive than doing BFS or DFS if you have to return the answer at the very end. But in practice, because the code is so compact We don't have to build the adjacency list. We don't have to write these functions for doing BFS and DFS repeatedly. You'll see that the actual running time in terms of practical performance would rival BFS or DFS, sometimes even beat it. But more importantly, when the graph is dynamically changing, there is no efficient alternative to using this union find data structure, where the union operation is implemented in the following way, where we are effectively doing a weighted quick union. Now, I didn't show the code for find operation, but it's basically the same compact code that we had earlier. We start from X. If we have to find the leader of X, we just keep walking up from X until we reach a node whose parent is itself, and that node is the one that we're going to return as the leader of X. Now let's look at a classic interview problem involving this union find data structure. Suppose you're told that there's a social network, something like Facebook, where there are n people whose IDs are given in this convenient range from 0 to n minus 1, and we have a list of entries in the log file which record the exact time point at which friendships formed, okay, direct friendship relationships formed between pairs of people. So here's a simple example. Suppose we are given that there are 6 people on this social network, and we are given a sequence of entries, and these have timestamp values corresponding to the time at which pairs of people became direct friends on this social network. So if we are given that n is equal to 6, we know that there are 6 people involved whose IDs are from 0 to 5. So let me show them like this. And at a particular point of time, 0 and 1 became friends. Then at a slightly later date, 3 and 4 became friends. And then at the third time point, 2 and 3 became friends, and so on. Now in this particular example, it turns out that the timestamp values are sorted, but in the problem itself they needn't be sorted. But even if they are not sorted, we can always sort these log file entries so that we are looking at what's happening across time. What's happening across time is that new friendship relationships are forming between pairs of people. Now these relationships can naturally be shown in the form of a graph. So when we look at the first edge between 0 and 1, we can denote the fact that 0 and 1 became friends by connecting them together with an edge. When we see that 3 and 4 then became friends, we can connect them with an edge. Then 2 and 3 became friends, we can connect 2 and 3 with an edge. And so what you see here is basically a bunch of friend circles forming, and these circles become larger and larger and larger when 1 and 5 get connected. Basically there is an edge added between 1 and 5, and at this point you can see that there are 2 different clusters, 2 different connected components that we have in this graph. Then there comes a point where 2 and 4 become directly linked to each other. So until this point 2 and 4 didn't directly know each other, but now they are direct friends on this social network. Then when 0 and 3 get to know each other, we have an edge added from 0 to 3, and you can now see that the number of connected components is basically 1. So even if 2 people don't directly know each other, they do have an indirect long distance acquaintance relationship with each other. And the problem is we want to find the earliest time at which everybody got acquainted with each other in this given data set. Now it's not necessary that everyone has to finally get acquainted with each other. Maybe the number of connected components at the end is more than 1, but if it does become 1, we want to find the earliest time point at which that happened. And as you can see here in this example, that earliest time point is basically this time point when 0 and 3 got linked to each other, reducing the number of connected components in this graph to 1. Now why is this a classic union find problem? Well, because think of what you would need to do if you were to use BFS or DFS. BFS or DFS don't have the notion of time in them. So even if by the end you find that everyone is acquainted with each other, that doesn't give you information about the first time point at which that happened. So you would have to go back and try out different time points to see when was the first time when everyone got connected together into one single connected component. And if we were to do this by doing this sort of linear scan backwards, we would basically take time in the worst case proportional to the time required for doing BFS and DFS times the number of edges, and that's clearly not efficient in comparison to doing union find, where we start out with all these people belonging to separate connected components, and then we simulate this process of friendships forming as each new edge comes in. As each new friendship is formed, we update the number of connected components dynamically, and the first edge which causes the number of components to reduce to 1, that edge, or rather the timestamp on that edge, is going to be the value that we have to return. That's the first time at which everyone got connected to each other. And this is something that in the worst case can be done in time that is proportional to n log n, which is going to be clearly better than the quadratic complexity that we had earlier using BFS or DFS. So let's go back and see what we need to change in the code, what we need to tweak in the code to solve this problem. So as before, we have two arrays, the parent array, which is going to store the pointers to the parents for each vertex, and the size array, which is going to store the size of the subtree rooted at each vertex. Both of these arrays are of size n, and they are initialized from 0 to n minus 1 and to 1s respectively. We are also tracking the number of connected components, which start out being equal to n. Now let's say that our list of edges, our edge list, is given in the form of a list of triplets in this variable called logs. So our logs file is going to have basically a bunch of triplets, which is going to be a timestamp value followed by a pair of vertex IDs or person IDs depicting the time at which u and v became friends. So our log file is going to have triplet entries of this form. Now if it turns out that our log file is not already sorted with respect to the timestamp, we can easily do a one-time sort at the beginning by sorting these triplets in according to the first field, which is the timestamp value. Now once we have that, we go through each triplet in the log file, and we will need to pretend here that u and v are becoming friends at this particular time. So we are advancing time, and so what happens when we see this this new edge coming in between u and v? Well, we need to find the roots of u and v. So we need to find the leaders, and the code for that is going to look the same. The code for the find function is going to look the same. And if it turns out that the two leaders are not the same, that means u and v belong to different connected components, then we have to compare the sizes of those two subtrees. If the size of the subtree rooted at u is smaller than the size of the subtree rooted at v, then we will decide to make the parent of root u be root v, and we will likewise have to change the size of root v to grow by the size of the subtree that has just come under it. And if this is not true, then we have to do the converse, that is, we have to make root u be the root of the overall tree. So we basically have to reset the parent of root v to be root u, and reset the size of root u to grow by an amount equal to the size of the newly acquired tree under it. But every time we do this union operation, we also know that we are reducing the number of components by 1, and so we can dynamically change the number of components, reducing it by 1. And since we are interested in the earliest time at which everyone got connected, we can directly add a condition here that if components becomes equal to 1 at any stage, then we will just return the timestamp value at which that happened, right? And since these timestamps are in sorted order, the first point of time where this happens is the point of time where we return. And what happens if we never return? Let's say we go through each edge and maybe the number of components comes down a few times, but it never really becomes 1. Then at the end of this for loop, we would know that the number of components is definitely more than 1, because as soon as it had it become equal to 1, we would have returned earlier. So at this point of time, we can return the default value that's expected when we know that there are still multiple connected components in the social network. That means there was never really a point of time when everyone got acquainted with each other. So we return whatever the default null value is. And I'm assuming that it's a -1 for this problem.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your 3 webinar slot today